All right, so for chapter 3, we're going to talk about displaying and summarizing quantitative data. So when you collect data, it's better to collect a lot more data because when you go to analyze it, it's an accurate reflection of the population. So we're going to talk a lot about samples and population. There are close to 8 billion people on planet Earth, and if I wanted to figure something out about people, I could never measure 8 billion people. What I could do is maybe measure 1,000 people, and if I do my measuring right, I can make some sort of inference to the general population. So the sample is the small amount that we measure, and the population is the big amount. Now, population means the total. So you could do this with cars. It doesn't necessarily have to be people or animals. It could be anything. But summarizing the data will help us to look, even still, 1,000 people, that's a lot of data, okay? So, and then without the summaries of the data, it's hard to grasp what the data tells us. It's just numbers if you don't organize it and analyze it and display it in a certain way. So the best thing to do is make a picture. We can't use bar charts or pie charts sometimes for the quantitative data because it's so massive. And since those displays are usually used for categorical variables, usually, okay? So anyways, so what does this mean? Well, we could do, one thing we could do is a thing called a histogram. And that's just displaying what we call a distribution of earthquake magnitudes in this example. So a distribution in histograms is a way that we can kind of look at the data graphically and not get too overwhelmed, especially if it's a large set of data. So this example discusses earthquake magnitudes, and then it says first slice up the entire span of values covered by the quantitative variable into equal width piles called bins, and the bins in each count, or the bins and the counts in each bin give the distribution of the quantitative variable. And so when we get to the slide, here's what we're looking at. This is the frequency on which something occurs, and then the x axis is the magnitude of the earthquake. So if I look here at the tallest one, it looks like there's almost 200 earthquakes that are short, just barely above 7, or maybe it's 7, depending. We really have to look at the data. But when I look at this, you could see this is what we would call a distribution, okay? The distribution shows me I got one here that's at 4. Well, it's more than that, you know, like this is 50. So there's a small amount here at 4. And so a lot of things in nature have this sort of distribution. It's referred to as like a bell-shaped type curve. But basically, there's going to be a mean or a median or a mode, and that's usually a measurement of some sort of center, and then it's symmetrical about that center. So the histogram plots the bin counts as the height of the bars, it's a lot like a bar chart, but it displays the distribution at a glance, okay? Here's the histogram for the earthquake magnitudes. So a relative frequency histogram displays the percentage. So it basically looks the same, except now we have the percentage. There's about 16% of all earthquakes that were measured in this study were either at 7 or slightly above 7. Does that make sense? And so what's cool about this, though, is in this way, relative frequency histograms are faithful to the area principle. You can get a feel for this just by looking at the graph. So this is basically the same thing as this one, except now we have a measurement of percentage. Okay? So your calculator will make histograms for you, and I'll show you how to do that in a separate video. But you should be able to go into the window setting and adjust the bin width. And again, I'll show you that in a separate thing. And you can experiment with the different bin widths on your calculator. Now, some textbooks will refer to those as classes. either term is okay. It depends on what you're doing. And then some of the data can be represented differently. So all this data is useful. But the nice visual about that is you could see where the center of the data is, like what's the average. And then you can see as you get further away that the occurrence is less likely. Does that make sense? Now, stem and leaf plots show a distribution of a quantitative variable, and they're kind of similar to histograms, but you can see their actual values. So if I look at this, if I look at this right here, I have a histogram, and see, I don't know what this value is, okay? But I have one thing here that's between 55 and whatever this is. But if I look at my stem and leaf plot, I have 56. And then my next number is 60. So what this is in the front here, these are like the tens place, and these are the ones place. And it tells me the data. So in other words, I have a 56, I have a 60, and so I forgot to read what it was, but these are this is a display of pulse rates of 24 women in the clinic. And this is the histogram of that. So one woman has a 56 pulse rate, another woman has 60. There are 3 women that have 64. There are 1, 2, 3, 4 people that have 68. 4 women that have 72. 4 women that have a 76. There are 4 people that have an 80. 2 people that have an 84, and 1 person that has an 88. Does that make sense? But notice that the distribution looks very similar to the bar graph or to the histogram shape, right? This one right here is the 80s and the 84s, and you have 188. And so the pattern looks basically the same. So how do you construct a stem and leaf plot? Well, first cut the data value into the leading digits. Those are called the stems, okay? And then the trailing digits are the leaves. And there's lots of ways you could do this. And we'll in your homework, you'll practice a couple different ways. But you use the stems as labels, like a label to the bin. And then you use 1 digit for each leaf to either round or truncate the data values to 1 decimal place after the stem. Don't forget to have like some sort of key so the reader that looks at this will know what the values mean, okay? So dot plots are kind of like a combo of both. It's just another way to do it. Your calculator can do dot plots. But a dot plot basically does the same thing. The nice thing about the dot plot is you get a feel for the distribution. So this is what we would call bimodal distribution, because you have some sort of center that looks like here and another center here. It's not really bimodal. I guess that's not the right terminology, but basically it looks like you have 2 separate distributions, okay? So the one that we're looking at, it's the Kentucky Derby winning times, and they're basically just plotting each race with a dot, and that's the winning time. So you got a bunch of people here that won faster, and I don't know what happened here. Maybe it was raining or something, but you could see that there's a huge gap. It says you might see a dot plot displayed horizontally or vertically. So before you draw, you got to think about making the picture. You also got to think about the area, right? Because do you want to look at this picture and have an accurate interpretation of the data? So now we have options of how we would display things. You just think carefully, like which one would be the best one. Before making a stem and leaf display or a histogram or a dot plot, you might want to check the quantitative data condition. The data are values that are quantitative variables whose units are known. Okay, you want to make sure that you're measuring the same unit for each variable. All right, so shape, center, and spread, those are things that are interesting or of value. That's the whole reason that we do statistics. So when describing a distribution, make sure that you always talk about 3 things: the shape, and that's like the curve or the symmetry. And then the center will stick out if it's similar to a normal distribution. And then the spread, we're going to learn about spread. The spread is like how far out it is. So what is the shape of the distribution? Well, does the histogram have a single central hump or does it have several humps? And the same, is the histogram symmetric or skewed? And are there any unusual features that stick out? So humps are generally measurements of some sort of central thing, a central measurement. So humps in a histogram usually show us a mode. Mode, if you recall, means that it's the value that's most often. So now a histogram with one peak is dubbed as unimodal. Histograms with two peaks is bimodal. And I wanted to be careful because if we go back to this, remember how Mr. Adams said that's bimodal? Well, I don't want you to get that confused with mode. Mode means something that occurs most often. If I look at this little line here, this occurs the most often in this little distribution, if I think of it as a distribution. When I look over here, I seem to have this thing that seems to appear the most often in this little distribution. This thing is one whole distribution. So we label this as bimodal, not meaning that it has two modes, but it has two peaks, okay? So anyways, back to bimodal. You can have multimodal depending on the data that you're collecting, okay? So this is an example of a bimodal histogram. It has two apparent peaks, okay? This doesn't happen all the time. When it does, it means something. This histogram doesn't appear to have any mode. It seems almost like it's a normal distribution, or not a normal distribution, but a uniform distribution. So if I were to pull a sample of this, I should almost always get the same thing. In other words, the expected value of something occurring, regardless of what the event is the same probability for each thing. So this is an example of rolling a die. So you guys are used to hearing the word dice. Die is just a singular for, two dice, all right? So a six-sided die, and then they're just keeping track of how many times you get a 1, how many times you get a 2, how many times you get a 3. And then this is a uniform distribution because you have an equal probability of rolling a 1. You have an equal probability of rolling a 2. You have an equal probability. So anyways, that's what that is. And then symmetry. So a histogram, if it's symmetric, can you fold it in half? Does the left-hand side look like the right-hand side? So this is a symmetric histogram because if I were to fold it in half, it's very similar on both sides. That is the most often occurrence of data that we collect in nature, okay? The height of human beings are this way. Sometimes you get some really short people and sometimes you get some really tall people, but once you get away from the average height, the distribution looks like this. How long people live, stuff like that, okay? If we were to collect any of that data, and then it occurs in nature a lot too.
Left or right one?
Well, I mean, it's never going to be perfect. But if they're very close, they're close. But now when we get to this next one, clearly there's a skew. So usually the thinner ends of the distribution are called tails. If one tail stretches out further than the other tail, then the histogram is said to be skewed to the side of the longer tail. So the blue one here is left skew. The one on this side is called a right skew, which is, it always confused me, and it always because you want to call it where the hump is, right? You want to call this one right skewed, and you want to call this one left skewed, but that's not the convention for labeling it. The one on the left is left skewed because the tail is longer. The one on the right is right skewed because the tail is longer on the right, okay?
So it's always the tail.
Yeah, so when you talk about labeling things as a skew, go by the tail, not the hump. Anything unusual? Does any unusual feature stick out? So when you look at skewed data, you go, why is it skewed? When you look at a normal distribution where it's symmetrical, you say, why is it that shape? If you look at a uniform distribution where they're pretty much all the same, you go, why? And it has to do with the probability of those things occurring, okay? What's the probability of somebody being 7 feet tall out of all of the human population? Not very likely. So as you get closer to one side, it's going to go one way, and if you get closer to the other side. So you should always mention there are scragglers or outliers. And those are things that are really far apart. And then you want to think about, are there any gaps in the distribution? Then ask yourself why. That Kentucky Derby one had some gaps. Why? Why were there two separate distributions for that data from the Kentucky Derby? I don't know. Maybe the data was collected over a long period of time. Maybe the horses are healthier and that gave you quicker times. Maybe it rained. You don't know. So then look at this one. What's unusual about this? Yeah, there's one little one away from the rest of them. Now, we might consider that to be, first of all, we would kind of think of that as an outlier, but there's more than one. But when I look at this right here looks like a pretty much symmetrical distribution, sort of. It's a very tight spread. But this is something going on. Now, what is this information about? Well, this is about people per housing unit. So for whatever reason, and this represents the number of cities, and so it's probably like the average for the city, people per housing unit, people per home or whatever. This is like 2 people. So it looks like there's like 3 to 4 cities where the average is 2 people. But then you've got this normal distribution. So, and I say normal, it may not be normal. Symmetrical is what I should say. So there are 3 cities in this leftmost bar that average about 2 people. Why is that? Who knows? But it's apparent by looking at it, so you can investigate the data and figure out why. Maybe there's an ordinance. Maybe everybody has to live in an apartment. Who knows? Maybe there's a city where they only have apartments, okay? So anyways, where is the center of the distribution? If you pick the single number to describe all the data, what would you pick? The easy way to find the center when a histogram is unimodal and symmetric, it's usually right in the middle. Now, if it's skewed, then you kind of pick out the center of where the peak is, right? Is the best way to describe it. So let's look at this one. What's the center of this distribution? Well, the middle value, if you look at this, it goes from like 3.6 to like maybe 9. So what's the middle of 3 and 9? Mathematically, it would be like 5 or something, right? Like if you look at this distribution, right here would be the middle, right? But there's something weird going on here. And these 2 are outliers, it looks like. So in the middle of the data, once the data has been ordered, that divides the histogram into 2 equal areas, it has the same units as the data, okay? And what you want is half above and half below. So it depends on what you're trying to look at. So what they're saying is, look, if I go from 4.6 to 8, maybe the middle is here, but there's something interesting going on here. That's why we have things like mean, median, and mode. Clearly, this tab here, right here, this is the mode. This happens the most often. The median would be in the exact middle. And if you add all this up and take the average, that could be a completely different center, okay? But the median is the exact middle. So we would take all this data and arrange it from the lowest value to the highest value. If it's 31 data points, what's 1/2 of 31? You would probably pick the 16th value, whatever it is, okay? So then, how spread out is the distribution? Well, the variation matters, and statistics is about the variation. So as we get into this thing, what we're going to do is we're going to collect a bunch of data, look at the data, and then figure out how wide the spread is, and that helps us to make a probability guess. So we're going to guess certain things. Always report the measure of spread along with the measure of center when describing a distribution numerically. So we're going to find two things. We're going to find the mean of a distribution, and then we're going to find the standard deviation, which is a measurement of the variation. Okay. So the range then is helpful too, because the range is the data. It's the difference between the maximum value and the minimum value. So if I go back to this chart, whatever this minimum value is and whatever this maximum value is, if I take those two numbers and I subtract them, that's going to give me my range. Now the disadvantage of the range is that a single extreme value can make it very large and not represent the overall data. Now this is where you got to be careful with collecting data. Okay, we'll do some examples where we'll explain why. The interquartile range is like this. It goes from the 25th percentile to the 75th percentile, so it's the inner 3/4. It's actually the inner half, because you're lopping off the first 25% and lopping off the last 25%. That's a great way to measure data, because the majority of the data in a symmetrical distribution is in that chunk. So quartiles just divide things into 4. One quartile of the data lies below the lower quartile, that's Q1. And then Q3 is the one that kind of separates the upper quartile. So if you want to know their interquartile range, you take the upper quartile and subtract it from the lower quartile. And that's a better measurement of the distribution. So what we're doing is the range can have outliers, so it can go from here to here. But then if we look at the distribution and we do the interquartile range, that's where the chunk of the data is. So it just narrows it in. By the way, the average of the interquartile range would be a lot of use mathematically, as opposed to you taking the arithmetic mean or average of the whole data set. Now, if it's normally distributed and you don't have a lot of outliers, they should be pretty much the same numbers for both. So let's look at this spread in the interquartile range. The lower and upper quartiles are the 25th and 75th percentiles of the data. The interquartile range measures the middle 50. So what we're doing is you have, this looks like an outlier. This kind of looks like an outlier. This looks like some information that's useful. But what they did is they literally looked at the values and they said the first 25% of the data occurs here. The last 25% of the data occurs here. We're interested in this stuff here, the stuff in yellow. That's the interquartile range. And you have a numerical value to find the 25th percentile. You have a numerical value that's associated with the 75th percentile. And the difference of those numerical values is 0.9. Okay? And this is going back to that data on earthquakes. Right? So on average, you're going to have some information here. So what does all this mean? Well, lastly, something that's very helpful is a 5-number summary. If you have a TI-83 or TI-84, I will teach you how to put the data into your calculator, and it'll help you double check all this stuff. You can do this by hand. We're going to do it by hand. Once that I feel comfortable that you've learned how to do it by hand, then I'll let you use your calculator. But it's a summary of 5 numbers. The maximum value, quartile 3. Yes, you got a question?
Yeah, so on the AP test, will we be able to use our...
Yes. Yep, on the AP exam, you can use those calculators. That's why I told you specifically to get a TI-83 or a 84. Okay? And it'll do all this stuff. And so the max and the min, quartile 1, quartile 2, and the median, which is the exact middle value. Okay? Anyways, that is something that your calculator just does. So to summarize what we're going to be doing in this chapter You can use a 5-number summary on small data sets. There's a lot of good information on that. Many AP problems provide you with only summary statistics. So it's important to recognize at the onset of the problem if you're being given the full data set or the summary. So there's a lot of manipulation of the data. You can get a lot from the summary, or you can calculate the summary from the whole data set. The problem with giving somebody the whole data set, it takes a long time to enter in the values into your calculator. So sometimes they just give you the other stuff. So now let's look at a box plot. That's one other thing that we didn't talk about, but it's just a way to graph, to make a picture of the 5-number summary, okay? So basically what you do is you're going to draw a single vertical line, and this could be horizontal too. Your graphing calculators will do this horizontally. But you could draw a vertical line and spanning the range. Draw short horizontal lines at the lower and upper quartiles. So this is the number summary. The max is 9.1. The minimum is 3.7. And what they're saying is, I'm pointing to the screen, but you guys can't see me point to the screen. This right here is the upper, this is quartile, the 3rd quartile. This is the lower quartile. And this is the median. So, and then you could draw, you're going to draw a straight line. That's why it's called a box and whisker plots. So these are the whiskers. So this is the maximum value. This is the minimum value. This is quartile 3, quartile 1, and the median. Now a normal distribution will have a box that's in the middle. Well, you can see it, but when you can read a box and whisker plot very similar to the way that you would read normal distributions. But anyways, then you can add the outliers. Oh, I kind of skipped over this. So the whiskers don't go all the way to the max. The whiskers are going to be, the upper fence is going to be 1.5 IQRs above the upper quartile. Okay? So whatever your interquartile range is, you're going to multiply that by 1.5, and that gives you this. Okay? Above and below the quartile ranges, right? So this is the 3rd quartile, and the distance from here to here is 1.5 times the interquartile range, and the distance from here to here is the upper and lower quartile range. And then lastly, this is where the whisker kind of thing comes from. Any data point that's outside that, you just put a dot, okay? And your calculators will do this for you automatically. So this is the data of our earthquake magnitude, and this is the median. This is the 1st quartile. This is the 3rd quartile. From here to here is 1.5 times the interquartile. From here to here is 1.5 times the interquartile, and that's the distance from the quartiles. This is quartile 1, quartile 3. And then they just plot the points that are outside. Any of the dots is considered kind of an outlier, okay? You can see the skew on this because where's my box? Is it right in the center? No. Where's my median? Right in the center? No. So if you have a normal distribution, your box is right in the center. And the median is right in the center of the box. So this is skewed slightly to the left. And you have more outliers out that way too. So lastly, you can summarize symmetric distributions or find the mean. And we'll go over some of these in a second after I'm done going over this PowerPoint slide. But we have symmetric data. There's an alternative other than the median. If you want to calculate a number, we can average the data. We use the Greek letter sigma. That's this letter right here. And that represents the sum. So this is also called summation notation. Did you guys learn summation notation in pre-calc? Is there anybody here that has not learned summation notation? Okay. Oh, well, I'll teach it to you. But basically, you're just going to add up all the numbers and divide them by the total numbers. And that's a fancy math way to say that, okay? So the summation is you just take every point, data point, and add it up. That's your total or your sum. That's why they call it a summation. And then how many, whatever the data set, how many ever points you have, that's what you divide by, which is the arithmetic average. But this is a little more formal notation, okay? So the mean then feels like the center because it's kind of like a balancing point for the histogram, okay? It's the arithmetic average. So because the median considers only the order of the values, it is resistant to values that are extraordinarily large or small. So if you have some crazy outliers, that'll have a huge impact on the mean. But it doesn't have an impact on the median, all right? And then if you choose between the mean and the median, start by looking at the data. If the histogram is symmetric and there are no outliers, use the mean, okay? So we're looking for measurements of center because that's usually where it's most probable that that's the value that'll have an impact on things. So if I want to make clothes for people and I want to know the average height of a human being, I'll collect a bunch of data, I'll look at the median, I'll look at the mean, and then I have to make a determination what is the average and then go from there. I'm going to make something smaller because the distribution says there are some people that are shorter. I'm going to make some things that are bigger because it's going to say some people are taller than the average, okay? And but I need to know the center because that's what I'm going to make the most of. So that's what we're talking about. Do I use the median? Do I use the mean? How do I know? So the spread has a lot to do with it, and that's basically, we measure that by the standard deviation. The standard deviation is how far are the data values from whatever center I choose, all right? So if I take the average height of somebody, what do you think the distance on that spread would be? The average height, I think, for men is like 5'6", 5'7" or something.
It's 5'9".
Is it 5'9"? That's the average height
Of a man?
of a man?
Yes.
Okay. So then 7 feet would be really, really, really tall. So that means you're probably within about 6 inches. So that's 6 inches from, and 5'9" would be what? 69 inches? Plus or minus 5 inches. So we can use some mathematical data that lets us know what the spread is. That standard deviation lets us know how far we go for 1 standard deviation, 2 standard deviations, 3 standard deviations. It's kind of hard to explain without doing the formulas, but basically it's a measurement of the spread. If you have a higher standard of deviation, you have a higher spread. A low standard deviation means you have a narrower spread, okay? Since you add all the deviations together, they would equal 0. And anyways, I don't want to get into the applications. This is how you would find the variance. And the variance is, we'll do some example problems of this, but this is the formula. The variance can be positive or negative, all right? And that's why we square it. So if you square something, it doesn't matter what the value is. In other words, you could be a couple inches shorter, you could be a couple inches taller, but we're measuring the distance from the center. And then the standard deviation is just the square root of the variance, right? So we square things and take the square root, which essentially just gives us all positive values. So if I measure my height and compare it to somebody's taller than me, and we go and find the difference of it, they might, I might be an inch or 2 shorter. But if you square -2, that gives you +4. And then when you take the square root of +4, we take the principal root, which changes it to 2. That's why we do that. So anyways, a higher standard deviation means that you're going to have a little bit bigger interquartile range. So when telling about quantitative variables, you can start with a histogram, dot plot, stem and leaf plot, and the then look at the data, okay? Now we're kind of, this is what we can tell by looking at the data. The shape of the distribution along with the center and the spread. If the shape is skewed, report the median and the IQR. If the shape is symmetric, report the mean and the standard deviation. So these are different applications that you would use in most cases. If there are multiple modes, there's got to be a reason why. And then you could even separate the modes and do this work within the different modes. Clear outliers. Some people would like toss out the outliers, so you do all the stats with the outliers, then they toss out the outliers. It's not ethical to toss out the outliers and do the stats without providing the outliers. In other words, you could do the stats with the outliers and without and allow people to decide what data is important. But when you start picking and choosing what data you're going to use, that's just usually not ethical nor helpful. The median and the IQR are not likely to be affected by outliers, though. So if you have a distribution and you toss out an outlier, the median usually isn't affected, because if you have one outlier that's really low and one outlier that's really high, you could toss both those out and the median's still in the same place. Same with the IQR. They're usually fairly similar. So what can go wrong? Well, you make a histogram of categorical variable, and pie charts and bar charts should be used for categorical data, right? Now let me explain that. If I want to know how many kids like pizza, I'm measuring something, but I'm measuring pizza. If I want to know how many kids like cheeseburgers, I'm measuring something, but it's categorical. I'm measuring how many pizzas, how many, does that make sense? This is quantitative. How many cheeseburgers do you eat? How many pizzas do you eat? Now I'm going to be combining a bunch of I'm measuring data usually within one category. All right? If you go back and look at all these charts, we're measuring the magnitudes of earthquakes. Finishing times in the Kentucky Derby. There's one category, and we're measuring the quantitative value within that category. Okay? So what they're saying is, if you it won't be helpful if you use the wrong picture for the application. Don't use bars in every display. Save them for histograms and bar charts. Below is a badly drawn plot and the proper histogram for the number of juvenile bald eagles cited in a collection. So look at this. If you flip-flop the x and y coordinates, you don't really, I mean, which is right? Which one can you get the data from? You see that? So they're measuring a week. A week is when they make the measurement, but it's not really quantitative, right? It's not really a value that should have an impact. Maybe it does. It depends on what you're trying to figure out. So in other words, if I'm trying to figure out which week all these juvenile bald eagles are showing up at this island, I know it's probably about week 9. But now if I flip it the other way and I measure how many juveniles are sighted and how many they're sighted in which week, like if I don't get the variable right, the second one, there's nothing I can, what does this mean? Well, this is saying 2 juveniles were sighted. Is this the first week? Do you see how confusing that second one is? So that's what we want to be careful of. So if you accidentally make a mistake, guess what you could do? If you look at data and it isn't quite right, flip the axis. You probably did something wrong. Okay. Choose the bin width that's appropriate for the data. Changing the bin width changes the appearance of the histogram. This one has a very narrow bin width. There's a lot of useful data here. This one's not too shabby. You can still see it, but see how this one looks a little more symmetrical? And this is telling you something, right? So it really depends on what you want. You want to choose one that fits your application. And here's a long list. I'm not going to bore you and read it all, but definitely check it out in your notes as you're doing your homework. Okay. What did we learn? We learned that there's different ways to measure the center of a distribution. All right. We learned that you can display this data through a histogram, stem and leaf plot, a dot plot, box plot. You can summarize the distribution with different values, such as the range, the IQR, and standard deviation. We know that the median and the IQR, when distributed, can be skewed. Use the mean and standard deviation when the distribution appears to be symmetric. Okay. We learned to think about the type of variable that we're summarizing, and that's basically it. Quantitative data condition serves as a check that the data are in fact quantitative. All right. Categorical, you have more than one thing that you're counting, right? How many pizzas do you like? How many cheeseburgers do you like? How many slices of pizza does this person eat? One category, lots of measurements. The second one is more quantitative, okay? Any questions? Whew, that's a lot to